Welcome. Today we're going to be talking about this book from Professor Olivier de Weck, Professor of Aerospace and Astronautics at MIT, Massachusetts Institute of Technology. So this is Technology Road Mapping and Development, a quantitative approach to the management of technology. Some of you will remember I interviewed Professor de Weck when this book first came out in 2022, and you can see that interview. I'll put a link in below where we talked about the motivations behind the book and Professor de Weck's experience at Airbus, which then was fed into the book along with a long experienced career involving academia and various companies. And a few weeks ago, we did this previous book, Engineering Systems, which came out in 2012, which is also very interesting. It's today's one's much thicker than the previous one. There's a lot to get into with this book. And before we start, I've got a spare copy. So if you'd like to be eligible to have the spare copy, it's literally here. It's packaged up in a box, ready to go. If you would like that, or would like the chance to get that, then leave a comment on the YouTube channel below, and I'll pick one of the commenters. So do that. The instructions again below they're in the description, and you should do that. It's a very good book, and you will like it. Okay, so let's get into what we're talking about. So I formulated the overview of this video in the form of questions, and we'll answer each of those questions together through the contents of the book. We won't be looking at all the detail. There's over 600 pages here, and it's 638 pages. So what is the central idea or argument in the book, and why does it matter? So the key idea is that there's a process that has been proposed, and Ollie has implemented at Airbus and various other organizations. NASA is now also implementing it, and that framework, I use more precise language, is that of the Advanced Technology Roadmap Architecture, ATRA. So that's this, and so that's very hard to see, likely, because it's very small. But this framework is used throughout the book, and at the beginning of each chapter, the framework is shown, and then these little red boxes indicate where we are on the framework throughout the book. So this is, I've just picked one at random, Chapter 2, Technological Milestones of Humanity, and therefore that's where this is, this little red box. If I pick another one at random, next one I can find of this ATIA framework being shown. This one. So Chapter 11, Systems Modeling and Technology Sensitivity Analysis. Again, the various piece of the framework that is important for that is highlighted. And this makes it very, I'm going to say easy to move through the books. It's quite a detailed and hard concept to understand. It's simple questions that are asked that build up the framework, but there is it is comprehensive. But navigating around, you don't get too lost because you're always referring back to this framework as a map to guide you. So the central idea of the book is all around this proposing of a rigorous and structured approach to technology planning and road mapping, and that contrasts, I guess, from a non-rigorous and non-structured approach, which is surprisingly common, even in large technical organizations that are developing very advanced technology. And that framework, the Advanced Technology Roadmap and Architecture Framework, ATIA, is that which is proposed, and it aligns technology with the strategic goals. And so just to move through the steps that are proposed in that framework, so we have a series of inputs, the steps that are run through, and then the outputs. And the steps at the core, so that core sort of spine in the middle, are step 1, where are we today? Step 2, where could we go? Step 3, where should we go? And step 4, where are we going? And they sound like sort of simple questions, but behind them is a series of tools and methods that you use to elicit them out from the organization and ensure that everything is connected together in a way that's consistent. Because clearly, if you're developing a large scale technology that's integrating many other sub technologies, all these things have to work in concert with each other. Thinking of like aircraft, for example, the development on the engines and the fuselage have to be somewhat in concert as and the wings, such that all these things can be integrated together. And an additional argument in the book is it emphasizes the need for objective, data-driven decision-making in technology management, as opposed to ones that are maybe more based around opinion, rather than something that is data-driven. Okay, so that should provide a bit of a sense of what's that central argument of the book, and we'll now sort of look more at the overview of it. So how is it organized? Well, as I mentioned before, this diagram is used multiple times and then highlighting in red to sort of guide you through, almost a bit like if someone had a PowerPoint presentation. This would be a common style to keep bringing the same slide up and then show where within that framework which we're talking about at any moment. Then the book is divided up into, all of the chapters are classified as one of 3 things. They're either a descriptive chapter, a prescriptive chapter, or a case study chapter, with the descriptive essentially meaning we're describing things the way they are, prescriptive being we're describing things how they should be, and then the case studies are those real world examples of how such a framework can be applied. And all of the chapters are very useful, but I think you could likely jump between them based on what's important for you right now. So there's a piece on intellectual property. That's, of course, very important, likely for everyone, but at any one moment in time, it might not be your highest priority. And so you could jump to that if it was, or to another one. But also there are clearly chapters on technology road mapping, which is the title of the book, which you likely need to read rigorously and understand, as that's really the foundation of the entire framework. So on the descriptive side, we've got several chapters. Sorry. Chapter 1, what is technology? Chapter 2, technological milestones of humanity. Chapter 3, nature and technology. Chapter 4, quantifying technological progress. Chapter 5, patents and intellectual property. Chapter 7, technological diffusion and disruption. Chapter 19, impact on technological innovation on industrial ecosystems. Chapter 20, military and intelligence technologies. Chapter 21, aging and technology. And Chapter 22, the singularity, fiction or reality. So see here, in the book, it covers right from sort of early people, but before maybe when we think even technology exists, right out to the far future, with speculative things that we often only think about in science fiction, at least day to day. Then the prescriptive side, and this is where the bulk of today's video is really going to focus on how we can actually apply these to our work and our projects. So on the prescriptive side, we have Chapter 8, technology road mapping. Chapter 10, technology strategy and competition. Chapter 11, systems modeling and technology sensitivity analysis. Chapter 12, technology infusion analysis. Chapter 14, technology scouting. Chapter 15, knowledge management and technology transfer. Chapter 16, Research and Development, Project Definition and Portfolio Management. And Chapter 17, Technology Evaluation and Finance. And then these are all pulled together with 4 big case studies, with case study 1 on the automobile, case study 2 on aircraft, case study 3, the Deep Space Network, which is NASA's global system of communicating with very deep space spacecraft, such as the ones that have now gone beyond Pluto. And then case 4 on DNA sequencing. So it isn't all, the book isn't simply one focused on, say, more mechanical things or aircraft things, aerospace things. There are also aspects on biological things. Okay, so what is the history behind the book and where does it come from? There's a nice foreword at the beginning from Paul Eremenko, who was at the time the CTO, the Chief Technology Officer of Airbus, the global aircraft maker. They're number 1 at the moment, or maybe number 2, between them and Boeing in making commercial aircraft. And it describes how they were, him and Professor de Weck were sat together, and there was a challenge that there lacked really sort of anywhere a structured technology planning process. There was a sort of lack in a rigorous technology planning process at scale. Things were mainly done via qualitative and intuitive decision making rather than that of data driven. And there was a strong need for a comprehensive technology planning framework. And so Professor de Weck took 2 years out of his position at MIT to go to work for Airbus to develop that, and that's where the book has come from. And today you can take the MIT course on technology road mapping. You can do it online, and it would be likely very good for you, especially if you find that this is highly resonant to your day-to-day work. So, as any good book will do, even the very fundamental terminology in the title is explained in detail. And so it can be easy to sort of, I imagine many people have in their mind what a technology roadmap is and what technology road mapping is, but importantly, there is a description of what even technology is. So question 4, what even is technology? So the answer provided in the book, there's a short version and a long version, and then we can sort of go on from there. So the short version provided is technology is both knowledge and deliberate creation of functional objects to solve specific problems. So functional objects to solve specific problems, and it's both knowledge and the deliberate creation of those functional objects to solve specific problems. The long version is technology is both knowledge and physical manifestation of objects and processes in systems deliberately created to enable functions that solve specific problems defined by their creators. So remember, it's all about functional objects that solve specific problems. Now, on the origin of that definition, so the term technology originated in the 19th century, meaning the science of craft. And so that involves both knowledge and the physical creation of objects to solve the specific problems. So we end up with this sort of dual nature between technology being both the understanding, the knowledge, and the application, which is the physical manifestation of the techniques and skills and methods to achieve a particular purpose. So it's important that we remember there is this knowledge component and the physical manifestation piece. And we can think of, I imagine in your mind, you could think of things where we perhaps know that something ought to be able to be made as sort of knowledge, like think of when they were developing the atomic bomb, but it hadn't actually been realized at that point. And when both of those have come together, we have a technology, we had a working atomic bomb. Okay, and so an example provided in the book is the refrigerator that everyone will have in their home, when that it uses the thermodynamic principles of the Carnot cycle and the purpose is to keep food cold, which is its function. So we have to have that knowledge, which is the Carnot cycle, but we will then also have to actually embody it in a functional object, which is an actual refrigerator. And just a little aside, I know many of you are interested in OPM, object process methodology, and if you want some examples of real life OPM diagrams, there are plenty in this book. There's very good use of OPM. I'll just find some nice ones. So we here on that side. You can see there on your left-hand side, figure 1.9, comprehensive technology management framework shown in OPM. So those of you who are familiar with reading OPM and OPL, you'll find these diagrams to be a very effective way of transferring the knowledge that's contained in the book into your own mind. And as I said, I think these could be some nice examples for you out there who are looking for more examples of OPM. And those of you who don't know what OPM is, I've got loads of videos on my YouTube that you can go off and see, and there's a course as well that you can take and learn about these things. It's a language. If you're familiar with SysML, you might view that on UML. Okay, question 5. What is technology road mapping? Why is it important? And what are its core components? So at its core, the sort of a basic technology roadmap is shown in figure 8.1. So I'll show you what that is, and that'll at least sort of illustrate in everybody's mind what we're talking about. I'll just find that. Figure 8.1. So here we have time running from left to right, and we have two swim lanes, the blue one, which is technologies, and products along the top. And they're sort of linked together. So there we have three things. We have time, technologies, and products. And the caption there says, a simple technology roadmap, linking technologies blue at the bottom against the products that will implement them, the red at the top, along a timeline. Interdependencies exist between the products and technologies. It says the source there is from Bernal 2009. Okay, so I wanted to show you that, so at least in our heads we have an image as to what a basic technology roadmap looks like. So from the definition in the book, it says a technology roadmap is a plan that shows which technologies will be used by which current or future product or service or mission, and by when those technologies will have to be ready and at what level of performance. So the key idea is it has to show time. So when, that was a key word there. So time, and then technologies, and we've already had our discussion as to what the word technology even means, and then products that will use them, because often a technology alone isn't a product that can be used by a user. So a technology roadmap is a plan that shows which technologies will be used by which current or future product, and by when these technologies will have to be ready and at what level of performance. So again, let's just look again at that diagram in the corner. So we've got time, we've got technologies, and we've got products, and we're showing interdependencies between them. Key idea there. Okay, and what is the purpose of it? So the main point of technology road mapping is to give stakeholders a sense of the direction and ensure that R&D resources are deployed in a targeted manner. The purpose of technology roadmaps in an organization are to, one, show the relationships across technologies, capabilities, products, services, and needs. So relationships as well as interdependencies on that roadmap, simple roadmap diagram I showed you. Align the investments in technology and in new development of new capabilities and future needs. So as we saw in the example, we might have like that one there. There's a double arrow, so one technology is going into potentially two products there, and map technologies to products, missions, and services, and define a timeline for the maturation of the technology adoption. So that's what a simple one is. And if we remember, the subtitle of the book was A Quantitative Approach to the Management of Technology. So that figure 8.1, which I've lost, that could ultimately be created without any quantification. Like you could just draw that on a whiteboard or in a PowerPoint slide, and that is done. And that's perhaps not optimal for your organization. It might be better than nothing potentially, but it might also be more dangerous than nothing, because it can give sort of a false sense of security that we have this defined roadmap, even though it might be kind of nonsense. So it says here, from my notes, more advanced technology roadmaps contain models of the needed technologies across multiple levels of decomposition and have clear links to the figure of merit FOM targets. So the figure of merit is then a very key idea. That is why it is even in the subtitle, A Quantitative Approach to the Management of Technology. And for myself, like in my work, the figures of merit are a very, very strong way of advocating for doing rigorous technology road mapping and for avoiding false promises about nonsense technologies that cannot be developed. So that was us answering what is technology road mapping, and what is important, what are the core components. So the core components, really to hammer it in, is we need time, we need technologies, and we need products, and we need some sort of interaction between them. And this ends up looking like what we might think of, not quite a Gantt chart, but something a lot similar to that. So question 6, what is a quantitative approach to the management of technology? And I have 6 points here. So data-driven decision-making, mathematical and computational models, figures of merit, FOMs, uncertainty and risk quantification, optimization of technology portfolios, and technology sensitivity analysis. So all of that is essentially requiring us to use numbers, and ideally numbers that are justified, well, not just ideally, very importantly, are justified off of rigorous modeling and assumptions that we can defend and that others can review. And it allows us to, someone can bring in an idea, and we're not just judging it by who brought the idea, we're actually assessing them based on the predicted performance and things like that. I think it'd be worth, at least on the figure and merit, diving a little bit deeper into that, because I find it to be very, very helpful. And those of you who've watched the interview with Professor de Weck know that we looked at the following chart in quite a bit of detail. So this is figure 8.2. So figure 8.2, just to get a sense, is a chart that shows two important figures of merit of a solar electric airplane. Now, just think in your head, what would be, how would you judge the performance of a solar electric aeroplane? So this is an aeroplane that flies using the energy of the sun, and you could think, well, in an ideal world, that might even be able to fly indefinitely. It could fly over a area of interest and do surveillance using cameras and beam that information back down like a spy satellite, but at a lower altitude and with more with control. Satellite is moving in the under an orbit that we can't just sort of change willy-nilly like an aircraft. Okay, so think about, for a solar electric airplane, so we've got in our mind, we've got this airplane and it's flying and it's powered by the sun. How would we compare several different designs of aircraft? And the two figures of merit that are pulled out in the research here are, let's get this right, endurance in hours and payload in kilograms. Which I think you might consider are two good figures of merit for a solar-powered aircraft. So endurance in hours, so that's how many hours can it fly before it's got to land or crash or isn't flying anymore, versus payload, kilograms. So that payload would be likely cameras or sensors and things of that nature. And likely more of those, so more endurance and more payload, is likely a better aircraft. And to do that, a whole load of technologies would be needed, batteries, solar panels, things like that. But we can roll up all of the benefits of those sub-technologies. So imagine a solar panel that is lighter and can be more efficient at extracting energy from the sun, would improve those metrics, and a lighter solar panel would mean that we have any weight saving could then be applied to payload, and endurance would be increased if we could pull more energy from the sun. And likewise, if let's say we had batteries that could be lighter, again, we would free up weight for a payload, massive payload, and batteries that could hold more energy would mean that we would, overnight when the sun doesn't shine, we would be able to fly under those battery conditions. Okay, so if you were to plot those two, those endurance and payload, and both would we want to maximize, more is better, we would end up with a chart like this, where essentially the top right-hand corner, so we want to maximize endurance, maximize payload, more of both, we would result sort of top right being the best design. But what Professor de Weck's done is he's put on here, on this chart, several different design of aircraft, both real ones and some speculated ones and cancelled ones. And the benefit of this is we can see, first of all, where the state of current technology is. So if we plot let's say, we work for a particular aircraft company, we could plot our particular design and we could plot our competitors and see how we compare. But we could also plot where we think technology can push us based on, say, a new generation of solar panel or something of that nature. But also, if we've placed ourselves on a target that is likely to be feasible. And so in the very top right, there's a thing called Boeing Solar Eagle cancelled. And this is way out from the others. Now, if you were a program manager on Boeing Solar Eagle and you did this plot and you saw that you had performance that is well beyond any others and any other proposed one, you could sort of think of two things. You could think, one, wow, we have some technology that really is nobody else has, because we're predicting or we're attempting to do something that's well beyond others. That might be true. Or it could be true that marketing or other pressures, or somebody has just suggested this would be really good if we could do that, has put it there, and there's no credible plan to get there. It does say cancelled, so it suggests that this was never built. which is a shame, but maybe that was kind of predictable if you're trying to do something that's so far beyond what anyone else has done before. It seems sort of kind of unlikely that you would do that unless you did have some secretive technology, some very advanced thing, and even then you probably would want to show a credible path to get there. So that was a bit of a diversion or deep dive into figures of merit and why they're very important. I think certainly what I do when I'm engaging with a technology project is to try and define what are those very key figures of merit for the particular system that we're developing, so that we can seek to maximize those or minimize, depending how you think about it. So, the weight of the system you might consider you want to minimize. So this is very important. So that is one way in which we can add a quantitative approach to the management of technology. And that's really where the book moves beyond the simple technology roadmaps that have been used very effectively, but can lead to false hope that we're able to develop anything. And it might be worth just thinking in your own mind about other sort of technologies that maybe suffer from something similar. I was thinking of the whole Elizabeth Holmes Theranos scandal, I guess, where it was a attempt to create a human disease diagnostic machine using only a few drops of blood. And if you were to, I haven't done this, but if you were to draw the figures of merit for such a system, it would have been apparent that what they were trying to develop was incredibly far beyond what had been done before. And I don't want to be pessimistic and say you shouldn't be trying to do things that are well beyond what has been done before, but you do need a credible plan of how to get there. And I believe from all the court cases, they didn't have that. And it went into the world of fraud and things of that nature. Okay, so what is question 7, what is the Advanced Technology Roadmap Architecture, ATRA, ATRA? So that is the comprehensive framework that is proposed in the book, and that really is the core of what everything and all the ideas in the book hang off. I will just show you again so that we do remain on the same page, literally. So that's it. And it's got these 4 key steps in the core spine. 1, where are we today? And to do that, you need to be using technology, state-of-the-art and competitive benchmarking. Where could we go? So this is technology systems modeling and trends over time. And both of these are sort of predicting things based on figures of merit. Question 3, where should we go? So this is your scenario analysis and technology validation. And question 4, where are we going? So this is technology portfolio validation and optimization and selection. Yeah, so that's the core framework, and yeah, you can use it to really systematically manage your technology in a quantitative way. So what are the case studies we have in the book? So there's automobile case study, aircraft, deep space network, NASA and JPL, DNA sequencing, and for those of you who find maybe it harder to learn from just the raw abstract idea, and prefer to dive into a case study, you can do that. You can just go straight to those case study chapters, review those, and then maybe move back to the abstract ideas. But additionally, there's lots of examples in each chapter of refrigerators, the electrical grid, electric motors, steam engines, printers, beavers, the animal who build dams by felling trees. and they move them around. There's several where I live, and they're quite interesting to see how they can build these structures. It even talks about how they teach each other to do these things. It's quite interesting. Mars base, so colony on Mars, cyborgs, Moore's law as an example of figures of merit. The famous transistor performance doubling, steel making, solar panels, solar powered aircraft. We spoke about turbojet engines, coffee cups, and mouse traps. So there's a wide variety. There's a whole load more as well. I just want to give you a taste of things. Question 9, how does technology road mapping fit into the broader context of systems engineering? So we've got, I was thinking about this, and these are my thoughts rather than sort of out of the book, but an integration with the strategic goals, especially at the sort of business performance level, the support of decision making. Systems engineering likes to frame itself as being able to provide the evidence to support decisions, and I think that the framework presented in the book is also, especially that quantitative section, very important. Modeling and analysis. Systems engineering is often integrating the multiple domains such that we can have an integrated model of our system, and being able to provide that and be able to provide the prediction based on simulation of certain alternatives is very, very important. When we talked about that solar aircraft plotting the figures of merit, a lot of that is speculative, and so being able to do rigorous modeling and analysis is very important for then creating credible figures of merit charts. And then additionally, systems engineering can support this idea of technology infusion, and whether that be through systems integration. We have a new technology, how do we then infuse it into our existing technology? People in military and defense stuff are often having to do this a lot because they have very long life systems. You think of submarines and aircraft carriers, like the actual hull may live for 50 years, but then various technologies that get embedded within it, be it the radar or missiles, things like that, they will be being updated on a more frequent basis, and for example, we might think of these new laser technologies to replace potentially interceptor missiles, and so they would need to be integrated into an existing system, and so that interface between systems engineering and the more technology road mapping can be very important for showing how a potential technology could be integrated into our existing system. So when I was talking about using lasers as a alternative to an interceptor missile, those lasers may have very high power requirements, and so the systems engineer who's likely to do that integration can then be feeding back into that road mapping team with regard to the need for there being a certain energy budget that they can support for this potential new technology. Okay, so question 10. What are the benefits and challenges of implementing technology roadmaps? So I thought of three benefits and three challenges. I think on the benefits side, the strategic alignment, improved decision making, and improved resource optimization. And by resource optimization, essentially killing technology developments that are not going to be feeding into our overall strategic goals. People often talk about there being various sort of hobby horse technologies under development in big organizations. What I mean by that is a technology that somebody has their own strong emotional attachment to, but isn't actually going to contribute to the overall strategic goals of the systems that are trying to be developed. So using such an approach, the quantitative approach advocated in the book, it can be easier to identify ones that are promising and eliminate those that are not. And then on the challenges side, I think it's harder to do planning that's rigorous like this. It's easier to do that non-rigorous, non-quantitative approach, but the outcomes and the actual quality is much higher doing the rigorous approach, but it is harder. Organizational resistance. So I said about sort of the hobby horse challenge. There will always be essentially a cohort of people who are resistant to this sort of quite transparent, quite quantitative approach, because it will essentially harm what they're doing, and so there can be a lot of resistance. And then an additional one is keeping all of this up to date, and the information overwhelm, knowledge management challenges that are on this. There's a whole chapter on knowledge management, but you can imagine the amount of, especially when you think of all the technologies embedded in an airliner and the various competing technologies and sort of how they overlap and things, the amount of knowledge to be managed can be phenomenal. Okay, and then question 11, how can I implement on my own projects? So I would suggest that you understand the core components of the book and the framework. So that's the core components on the diagram. So when you get your copy of the book, you should really make sure that you understand all of those blocks there. Then I would say you need to look at some examples. There are case studies in the book. Ollie's website, road mapping website, there'll be a link in that below. That has plenty of other examples. Last time I went on there was railway trains, and I think there was a hydrogen fuel cell one, and various ones, all organized in a table that is actually also presented in the engineering systems, this book, the 2012 book. The engineering systems, I'll just find this if I can remember. Yeah, so the famous table of classification of different functions, be it so you've got the processes of transform, transport, store, exchange, and control, and then of the 5 operands of living organisms: matter, energy, information, and money. And so all the technology roadmaps were classified into that table, which can then make it helpful for you if you're looking for an example that's more aligned with your own experience in your own domain that you work in or you're interested in. You take the course, an MIT course, again, link below. If you're interested in scenarios, I have a course on that, which you should also take. And if you're interested in OPM, when there's a lot of OPM diagrams, I have a course on that you should take. That will be linked below. And then another piece is this: you shouldn't do this as an island by yourself. This needs to be an iterative process with feedback, where you're getting on board the various stakeholders who interact with you regarding your system and your technology developments, as without that it can become sort of somewhat stagnant. So you need to regularly review and update and get that feedback and have people actually understand and to really take ownership that together we're developing this technology that will push our organization forward. Now, at the end of the book, there's some very interesting stuff on future trends. So on question 12, what are the future trends in technology development that are highlighted in the book? So there's a whole chapter dedicated to aging in technology, so older people and how society, especially Asia, Japan, Korea, China, and so Western world, so Italy, America, and the UK, there's a lot of talk around how society will on average be older. And there's quite an interesting chapter on how aging and technology can potentially improve things, but also challenges of technology adoption by older people is generally lower. And I think you can probably experience that from for your own lives. And then looking onto the further future, there's a whole talk around sort of singularity and the limits of technology. If people are really interested in sort of singularity stuff, we can look at some other books on that in the future. So sort of like stuff like this, and this is this is a collaboration of several people. But so if we want to go down that rabbit hole and the whole sort of Nick Bostrom stuff and will AI take over the world? We can do that. But within the technology road mapping book, so there's a clear distinction mentioned regarding sort of the limits of technology. So we tend to think of physics laws that govern sort of how the universe works and sort of computational limits. So sort of the fundamental physical law limitations of the speed of light. That seems to be a law that cannot be broken. So the limit of any technology is likely to be limited by that. In addition, sort of NP hard problems in computation, they may not be able to be overcome. But then we have ideas like quantum computers, and maybe that then becomes a way of jumping through that. And then a challenge of predicting when we will reach those limits, and how progress is often sort of in an S shape, it starts a bit slow, and then there are big jumps at the midpoint of that technology, and then it starts to taper off again when essentially the complexity of the system needed to increase its performance gets to the point where that in itself slows down the progress. And then I touched on singularity, so that's a concept that technology, and that's AI, artificial intelligence, becomes self-reinforcing to the point where it is able to essentially leapfrog humans and then improve itself to the point, to a place of no return. And then there's a nice section on sort of utopian versus dystopian futures, and whether there's a lot of science fiction that is focused on dystopian futures and how technology will lead to the downfall of human civilization. So if you think of your favorite science fiction films and books, there's a lot of talk of how essentially technology is the downfall. But then, of course, we can have utopian futures, and I think maybe many of you have read this book. This is a compilation of 3 books, but the sort of 3 Californias with Kim Stanley Robinson. So this presents the same location in Southern California, but under 3 different scenarios. One sort of utopian one, and if I recall, one very strong dystopian, and one sort of somewhat in the middle. And this sort of idea that where would technology go and how do we do the scenario mapping out? I talk a lot about in my course, and so you should look into that if that's of interest. Okay, so we've gotten through all those questions. I think now we should just look at the summary that Ollie provides at the end of his book, which is just back here, just so we check off that we've really locked in our minds the key ideas. Sure, here. Okay, so technology is not unique to humans. So there are examples that are provided in the book. Those beavers I spoke about earlier in the video would be an example. Technology progress can be rigorously measured and predicted. So that's those figures of merit. That's super interesting there. Road mapping is a helpful and necessary activity in a technology-driven organization. Yep, I think we can all agree with that. 4, when setting targets for technology development, it is important to find the right level of ambition and timing. We don't go be too ambitious and predict something that is not based on any credible plan. Road mapping is not, this is 5, road mapping is not in isolation, but in the context of technology management. So there are other functions that are important. I haven't touched on them in this book, but you can get into those in those other chapters, especially knowledge management, intellectual property management, technology scouting, and I think there's a chapter on industrial clusters as well. 6, technology does not deliver value on its own, has to be embedded in a parent system and have beneficiaries and users. And I like that those core components of a technology roadmap of time, technology, and then products in which they're embedded in. I think that's an important idea. And then question 7, there are many open questions that are still not settled regarding technology. So yeah, if you're interested in doing that research, there's plenty to be done, which is very interesting. Okay, so we've gone through that. As I said at the start, I do have a free copy of the book. Here it is. It's all packaged up, ready to go. So if you want this copy, leave a comment on YouTube, and you'll then be eligible. And I will, pick one of those, and you can subscribe on the YouTube. You can also, if anybody wants my notes, you can get them as a PDF. You just have to put in your email address again down below on the, it'll be in the comment, the instructions how to do that. So I'll just be a one-click link. I hope this has been helpful for you. I'm just going to go over the definition of technology again, because I think that's actually a little bit of an important idea to really remember and close on. So the short version, technology is both knowledge and deliberate creation. So it's both knowledge and the deliberate creation of functional objects to solve specific problems. So if you do that, if you develop either knowledge and functional objects that solve specific problems, then you're in the world of technology, and therefore it's likely you need a technology roadmap if you don't have one already. Hope that's been helpful, and we'll see you soon.